I would like to welcome you. Start off, I worked for about 15 years as an engineering manager for the Atomic Energy Commission, Department of Energy, developing the fuels and materials for nuclear water reactors, the Santa Onofres, the Diablo Canyons, and the like. And then the liquid metal fast breeder reactors, called the LMFBRs. I'll refer to them as we get on. In about the mid-1970s, I returned to the farm from where I was raised and became involved with the Idaho water issues, predominantly the Endangered Species Act and its Idaho Endangered Salmon and Steelhead. If we have time, I will address it on that. My brief presentation is about the two issues, proposed NWAPA program and the energy for it, and then the water traversing through Idaho, a difficult task. NWAPA will require copious quantities of power for its proposed pumping stations and other purposes. There may be encountered overriding environmental concerns limiting the quantity of hydro plants that can be built, thus requiring other power sources, perhaps nuclear and maybe natural gas, which has recently become more abundant with this new fractionation techniques. Today's nuclear power plants, if built, can meet the proposed NWAPA energy requirement. They are environmentally green and they are safe. Natural gas plants, relatively cheap and expedient to build, still have a greenhouse carbon impact about 1/2 that of a coal-fired plant. We have 50 plus years of successful experience operating nuclear water reactors. These type of reactors are the 100 plus operating plants providing 20% of this nation's electrical power. Plus, these are the same concept of reactors that are and have been operating successfully in over 100 of our nuclear Navy submarines. Other nations are successfully operating these reactor types, with France, interestingly, leading the way where they produce 80% of their electrical energy from nuclear generation. Japan and France both moving heavily this direction, predominantly because they have absolutely no fossil fuels. I need to just digress a little bit from my speech because I'm going to talk about some isotopes and the fissioning process. The fissioning process is very simple in concept. It just gets ugly when you get into the details of it. Okay, but for those of you who are physics majors, what you have are three isotopes that fission. The first one is uranium-235. We have that in nature. The second one is plutonium-239, and that is a man-made isotope that comes from the fissioning process if you design your reactor right. The third one is uranium-233, and it comes from the irradiation of thorium, which absorbs a neutron and transposes itself through a couple of different isotopes to U-233. Each one of these isotopes have their own advantage, and you take advantage of that by the coolants and the design of the reactors to maximize the fissioning process. If you like uranium, you will love plutonium. It fissions about 25 or 30% more efficient. It produces more neutrons. The fissioning process is, you got an isotope. A neutron impinges on it. Three things happen. The atom breaks up and goes into two smaller pieces called fission products. And a tremendous amount of heat is released. Einstein's theory of relativity. E equals mc squared. The change in energy is equal to the change in mass. These two isotopes are just a little bit smaller. That's made up by the energy. Then, in addition, there are an average of 2 to 3 neutrons that are generated on each fission. And these new neutrons go out to cause other fissioning. That's the process. And that's what a nuclear reactor takes advantage of by the proper design and proper control. Okay, with that little education process, we have available uranium for fuel in the foreseeable future. A pound of uranium, as found in nature, has the energy equivalent of 7,500 barrels of oil, 1,500 tons of coal. The uranium in nature is 7/10 U-235, so all of that energy is available from that small amount of uranium. The other 99.3% is U-238. Commercial reactor fuel is usually enriched to about 6% U-235. We now store the 40 to 50 year supply of inventory from spent fuel from our commercial nuclear power plants at the power plant site because we have no fuel reprocessing plants operable. If processed, about 95% of the U-235 fuel that is in this spent fuel that's sitting in these reactor sites is available, and we have the technique and technology for processing. It's relatively simple chemistry. Why would you want to reprocess this fuel? The spent fuel of a 1,000 megawatt electrical plant over the 40-year period, where we've only used a small percentage of it, contains the energy equivalent of 5 billion gallons of oil or 37 million tons of coal. And we have the equivalent of approximately 60 to 80 of these plants to work from. So there is a tremendous energy resource just sitting there waiting to be used. And then lastly, there exists much enriched uranium left over from the Cold War weapons reduction actions, which can be blended down to make reactor fuel, whether you want it 2%, 4%, or 6%. The aforementioned reactors, that the 100 of them that I was talking about that are in operation, are called thermal reactors, and they use water to cool the nuclear fuel cores. Water moderates these neutron energies some, but a little plutonium production occurs. A neutron hitting the U-238 atom can absorb it and does absorb a lot of it and transposes into plutonium-239. Plutonium-239 is a tremendous weapons program or material. Ever fission is caused by a U-235 atom absorbing a neutron, which results in the average of this 2.5 to 3 neutrons that go available for new fissioning. The neutron energy produced in this water environment is enough to cause fissioning, but not enough to get significant breeding. However, if you replace the water with a liquid metal coolant, such as sodium, sodium coolant is much more heat transfer efficient, as you can expect from a liquid metal. And the beautiful part about it, it's opaque to neutrons. Go right through it. Sodium doesn't slow them down and change their direction or anything. In the absence of water, the resulting high energy neutrons of the fissioning can be absorbed by this U-238, producing plutonium-239, and which fissions even better than 235. The LMFBR, the liquid metal fast breeder reactor, is a next generation which can extend our fuel supply to over 1,000 years. We have 25 years of successful operation of the experimental breeder reactor in Idaho, the fast flux test facility at Hanford, Washington. The LMFBR concept, the liquid metal fast breeder reactor, it's as advertised. It can produce more fuel than it uses. The breeding times can be from 7 to 15 to maybe 20 years, just depending on the fuel type you use and the reactor design employed. The UK, France, Russia, and Japan have operating LMFBR demonstration plants today. The US has none. We canceled ours back in about the mid-1980s. It was being built at Clinch River at the Oak Ridge, Tennessee. And I can address this concept a little bit more in detail in the question and answer period. One of the problems of plutonium is the lack of reprocessing is associated. They did not want to accumulate copious quantities of it available for terrorist or militant organizations that could hijack it, steal it, or whatever. There is a concept that has been demonstrated in the United States called the integral fast reactor. And it is a simple concept in which the fuel and the reactor operate over here. There is a connecting device right over next to the plant where the fuel is reprocessed and then ships right back into the reactor. It never sees the light of day. It is unavailable to be stolen or heisted. How much longer? 5? Okay. Let me go quickly. The next issue of traversing the mountainous terrain of Idaho with the Nawapa Water headed south to the arid states. Idaho has more miles of salmon and steelhead spawning habitat than any other state. The adult fish must navigate from the Pacific Ocean up the Columbia River through 4 major hydro dams, then up the Snake River through 4 more major hydro dams to reach the birthplace spawning streams. 1 year later, the smolts that have been produced, they must return to the ocean through the same torturous route, and in some cases, the one-way trip is 800 miles. I point this out because the Nawapa concept proposes 14 dams on Idaho rivers that are critical habitat to the endangered salmon, steelhead, and other local fish and wildlife species. Granted, this Parsons study was done in the 1960s when none of us had ever heard of the Endangered Species Act. The proposed dams with their hydro plants and pumping stations are in or border on pristine and protected wilderness areas. There is even an ongoing effort to remove the 4 major Snake River dams, which produce 600 to 800 megawatts of electrical power from EPA, irrigation to someplace between 35 and 55,000 acres of farmland, and the barging of 700 miles from Lewiston to the Pacific coast for forest products, wheat, and minerals on the way transported to the Pacific Ocean. And in my opinion, and I point this out for the Nawapa people to take home with them, no proposed dams would be allowed on Idaho's protected rivers, Clearwater, Lockshaw, Selway, Salmon, or Snake Rivers. And alternative designs must be begun to be addressed and relatively soon, since this is the proposed primary conveyance route. The success of the Nawapa concept hinges on getting water through and around Idaho. In order that the Nawapa concept proceed and receive acceptance, it must be practicable and doable. I can only tell you it is going to take our best technical minds with strong public, state, Canadian, and congressional assistance to be successful. And I thank you.